This video is all about invariant points and lines. So invariant points are, funnily enough, the points that don't move when you do a transformation. So the coordinate xy, when I do the transformation, will get mapped to the coordinate xy. It won't move at all. So an example of this would be if I had to reflect in a mirror line, the points that are on the mirror, so for example this point here, this point here, this point here, this point here, or any of the points on this mirror line, in fact, any of those points would be invariant, they wouldn't move. So that's what we mean when we talk about invariant points. When I do a transformation, when I do a reflection, for example, these are the points that don't move. So you will often get a number of points that remain invariant, like I have here. There are a number of different points. In fact, there's an infinite number of points here that remain invariant, and they lie on a line. This is a line of invariant points, which is different to an invariant line that we'll come to shortly. If I have invariant points, then I know that when I do the transformation matrix ABCD to the coordinates xy, I will get the coordinates xy. Like I said, xy gets mapped to xy. Right, let's talk about invariant lines, because like I say, they are different to a line of invariant points. These are points that don't move, but they just happen to form a line. An invariant line, however, is where the line doesn't move, but points on the line can. So to give an example of that, if I were to reflect in this mirror line here, we can see that the green coordinate here has been mapped to the green coordinate here. It's reflected to there. The blue has been reflected to the blue. The black has been reflected to the black. And so what we've got here is a whole series of points on this line that have been reflected. But the line itself, this line here, when I reflect in this mirror line, the red line wouldn't move. It would be invariant. All of the points on that line would move. Like I said, the green gets reflected here, the blue gets reflected here. All of the different points on this line get reflected. But the line itself is invariant. So hopefully you can see the difference between a line of invariant points, where the points are not moving and they just happen to form a line, and a invariant line where the points on the line move but the line itself doesn't. So if the points move, then we can say that xy gets mapped to x dash y dash. It gets moved to a different coordinate. All the dash means, remember, is the image coordinates. So these are the new coordinates. Now this is the key thing then. Because it's an invariant line, both x and y will obey the equation of that line, and also x dash y dash. That coordinate is on this line as well, so that will also obey this equation, y equals mx plus c. So both sets of these coordinates would obey this equation. And again, representing this with the matrix equation, I'd have ABCD times xy would give x dash y dash. So that is the theory. We're now going to see how that works with 5 different examples, because this can be tricky. We'll start off with the simpler ones. So I've got matrix 2, -1, 1, 0. And I want to show that 5, 5, the coordinate 5, 5, is an invariant point under that transformation. Then part 2, I want to it asks me what can I say about the invariant points under that transformation. So if I want to show that 5, 5 is an invariant point, basically I just want to apply this transformation to the coordinate 5, 5, and hopefully I will get 5, 5 if it's invariant. So if I do that, if I apply the matrix to 5, 5, 2 times 5 plus minus 1 times 5 gives 5. 1 times 5 plus 0 times 5 gives 5. So we can see that the coordinate 5, 5 gets mapped to the coordinate 5, 5. Therefore, that coordinate is invariant under this transformation. Part I done. Part II, what can I say about the invariant points? Well, invariant points, I know, follow this equation. We saw that here. Invariant points follow this equation. So if I were to multiply this out, I'd have 2 times x, so I'd have 2 times x plus minus 1 times y equals x, and then I'd have 1 times x plus 0 times y equals y. So this is just multiplying that out. And I notice by rearranging the top equation here, if I just take x away from both sides and add y to both sides, this equation can be rearranged to be x equals y. And similarly, the bottom equation can be rearranged. In fact, it's already in the form of x equals y. So these are consistent. So what we're finding is all of the coordinates where x equals y are invariant. All of the points on the line y equals x or x equals y, the same thing, are invariant because these are the same, they're consistent. And just to show you what that actually means, what we're saying here is under this transformation, all of the points on this line, including the coordinate 5, 5, like we saw in part I, all of the points on this line, when you apply that transformation, they would stay exactly where they are. The 5, 5 would stay where it is. 3, 3 would stay exactly where it is, and so on. So that's example 1. Example 2 says determine whether this matrix has any lines of invariant points. So we're still talking about invariant points here, so I'm still starting off with that same equation. I'm going to multiply out like we did before. So I'm going to have 5 times x minus 2 times y equals x, and 3 times x minus 0.5 times y equals y. Rearranging the top equation, if I rearrange this, move the 2y over here, move the x over here, and then divide through by 2, I get this. Rearranging the bottom equation, I'll get this, and again, they are consistent. All of the points where y is twice the x coordinate are invariant. So yes, the points on the line y equals 2x are invariant. Example 3. We've seen 2 examples where it works. You can probably guess what's coming up now then. So we need to show that the transformation represented by that matrix has no invariant points other than the origin. Remember that the origin is always invariant with a linear transformation. So start off exactly the same as before, same equation, we're still talking about invariant points. So we're starting off the same, multiplying this out, 4 times x minus 3 times y equals x, 2 times x minus 5 times y equals y. When I rearrange the top equation, I get y equals x. When I rearrange the bottom equation, I actually get y equals 1/3 x. So in this case, we can see that they are not the same. And the only coordinate where both of these things can be true is the coordinate 0, 0. 0, 0 satisfies both of these equations, but no other coordinate will. Therefore, we can say that there are no invariant points other than the origin. So, we've done 3 examples on invariant points. We're now going to look at invariant lines, which, as you're about to see, is quite a lot longer and trickier. So we need to find the invariant lines of the transformation represented by that matrix. So notice we're talking about lines, not points. So going back to our beginning sheet, we're talking about this equation for invariant lines, where both xy and x dash y dash obey the equation y equals mx plus c. Right, this is going to be quite long, so pay attention. Right, we're going to start off with that equation. So we've got the 3, 2, 5, 6, x, y equals x dash y dash. The points x and y are being mapped to the points x dash y dash. Multiplying that out gives me this. Now, I know that the points x and y both obey the equation y equals mx plus c. They are on the line y equals mx plus c. So what I can do is I could substitute this mx plus c into the y here and the y here. So that's what I'm going to do. In that first equation, I've got 3x, I've got 2 lots of the mx plus c equals x dash. And I'm going to do exactly the same for the second equation. Instead of y there, I'm going to make that equal to mx plus c here. Next, I know that the x dash and the y dash, they also lie on the line y equals mx plus c. So I can also substitute all of this here instead of the y dash, and then all of this up here instead of the x dash, which gives this long equation. So like I say, the y dash, that's just all of this. The x dash, that's all of this. Now, I should probably remind you of exactly what we're trying to do at this stage. We are trying to work out what m and c are. We're trying to work out what m and c are so that we know what the equations of the line y equals mx plus c should be if they are invariant. So I'm trying to find what m and c are in this equation. Now, because you've got lots of brackets there, so let me multiply out some of those brackets. That's just timesing out the brackets here, timesing out these inside brackets here, and then multiplying out these brackets again over here to get that, all of that. Next, I am going to move all of this on the left-hand side over to the right-hand side. So what I've got here is I've got the 2m squared x here. I had a 3mx and I've subtracted 6mx from that to give me minus 3mx. And then I've got a minus 5x as well. I've also got the 2mc from here. And I had a c, but I had to subtract 6c from that to give this. So I've probably not explained that in the easiest way, but hopefully you can work that through and rearrange that for yourself to show that if you take all of these things away from over here, you do get this. You might have it written in a different order, but I have written it in this order because I know the step that's coming next, where we are going to factorise the x outside of each of these, and I'm going to factorise the c outside of both of these. And that is particularly useful because I know all of this has to equal 0. So I'm going to consider the general case where I think that has to be 0 and that bit has to be 0. I'm assuming that this is going to if the whole thing is going to equal 0, it's going to be 0 plus 0. I don't want to get into a very specific circumstance where I'm looking at this is equal to the negative of this. I'm talking about invariant lines here, so the general case of where lines are invariant. So I know this bit has to be 0, because it's the x coordinate, remember, is always changing, and if I'm making these equal to the negative of each other, then that is not going to work for all values of x. So this bit has to equal 0, and this bit has to equal 0 for it to equal 0. So, like I said, we're talking generally here. I'm not talking about specific values of x. This needs to work for all x's. So that means that this bit has to equal 0, and this bit has to equal 0. This bit over here could equal 0 when the 2m minus 5 equals 0, or when the c equals 0. Either of these can make this 0, but only this can make this whole bit there 0, because the x can't equal 0, if I'm talking generally. So let's consider this. So if I solve this by factorising or my calculator, I get these two values of m. Solving over here, again I get 5 over 2 here for m, or c equals 0 from here. So let's consider both of these cases then. If, let's do this one first. If m equals minus 1, if I'm saying that the gradient is minus 1, then obviously it can't be 5 over 2 here, which means that it would have to be 0. Let me just repeat that. If I am saying that the gradient is minus 1, then obviously the gradient can't be 5 over 2 from here. So the only way to make this bit here 0 would be if the c was 0. So what I'm saying is that when the gradient is minus 1, I know all of this will be 0. And if the gradient is minus 1, then the only way of this being 0 would be if c was 0. So y equals mx plus c, so y equals minus 1x plus 0. There we go. This is an invariant line. Whereas, if m was 5 over 2, then actually this bit here will be 0 no matter what the value of c is. So c can actually be anything as long as the gradient is 5 over 2. And again, let me just repeat that. If the gradient is 5 over 2, then this is already going to equal 0, and this bit here will already equal 0 as well. So therefore c can be any value at all. So in actual fact, we get an infinite number of invariant lines here. Y equals 5 over 2x plus c. It could be 5 over 2x plus 1, 5 over 2x plus 2, a whole series of different invariant lines. That's what we're saying here then. So when we do this transformation, the 5 over 2x plus 1, that would be an invariant line. Again, like I said before, the points on the line would move, so this point here might move here, or this point here might move here, but the line would be invariant. Or it might be 5 over 2x minus, I don't know, whatever, minus 3. C can be anything. So all of these lines that are parallel would be invariant under this transformation. Okay, fifth example, we're just going to, and we'll go for it a little bit quicker. We're going to do another one of those. This question is more or less exactly the same as the one we've just done, but with a little twist at the end. So, we can start off, same idea. We're talking about invariant lines, so we're using that formula. Expanding it out, we know y equals mx plus c. So therefore, if I substitute that mx plus c into here, I get this. And if I substitute the mx plus c into here, I get this. Now I know that these two coordinates here also obey the y equals mx plus c rule. So instead of writing this, I could write all of this. So this is this. Equals m times all of this plus c. Expanding those brackets, moving everything over to the right hand side, factorising the x outside of the front terms, the front three terms, factorising the c outside here, I get this. And then again, like I said before, we know x can't equal 0 generally, therefore this bit has to equal 0. And this bit over here has to equal 0, which can happen when either this equals 0 or this equals 0. Solving this quadratic here gives me those two solutions. Solving this linear equation gives me m equals 3, and like I said before, c could be 0. So if m equals 1, then it can't be 3, and so to make this 0, c would have to be 0. So the line y equals 1x plus 0 will just be y equals x. If m equals minus 2, then again m can't equal 3. Therefore c would have to be 0. So we get the line y equals minus 2x. This m equals 3 then in this case here is pretty redundant because m can't equal 3 because this would never equal 0 if it did. So we've got two invariant lines here. And just to show you what that transformation actually looks like, I've just tried to draw it out here. We have obviously our x and y coordinates here. We've got our original parallelogram here, A, B, C, D. And when I've applied that matrix to it, to this green parallelogram, it has transformed it to become this red parallelogram. We can see that A has been transformed over to A dash, B has been transformed over to B dash, C to C dash, D to D dash. So all of these points have moved. They are not invariant points, but they are still on the same line. A has been transformed to A dash, and that is still on the same line. It's still on the same line. This dash line here is the line y equals minus 2x here. And similarly, B is not invariant. It's moved, but it has moved to another point on that line. It's moved over here, that line being y equals x. And in fact, all of the points on the line y equals x, they've just moved to different points on that line. This point here would have moved to this point here. This point here would have moved to this point here. And in fact, you can see D has moved to this one. So all of the points on the line y equals x have moved, but the line itself has stayed exactly where it is. It is invariant. So quite a complicated, or can be quite a complicated topic, and there is a lot of algebra involved. Key thing really is knowing the difference between invariant points, knowing and an invariant line, the difference in the two formulae, and then remembering this process for working out the equations of invariant lines.